Welcome to our MATLAB tutorial channel. Today we are going to dig into an exciting project where we model, simulate and control a nonlinear RLC circuit with MATLAB. Let's break down each step of the project and understand the MATLAB code involved. Let's introduce the project. We begin with circuit that includes non-linear negative inductor or resistance of 240 ohm and a capacitance of 15 microfarad, all driven by a current source. This setup is especially interesting because of the non-linearity introduced by the inductor. So our first step will be the state space equation. We define the state space equation for our circuit. The inductor current IL is defined as IL is equal to 10 multiply sine k phi, where I dot is equal to 0.25 ampere point 0.25 ampere and k is equal to minus 1.2 and or this relationship introduces nonlinearity into our system, which we will address through local linearization. So let's develop our space equation for this nonlinear circuit, where the flux phi in the inductor that is defined as x1, one of the two states variable, has the following relation to its current. IL is equal to I naught sine into k phi, with I naught is equal to 0.25 ampere and a negative coefficient k is equal to minus 1.2. Without need of mentioning the voltage across this inductor, satisfy the Faraday law. VL is equal to d phi over dt. Circuit is already given, so as we know, state space equation generally represented by x dot is equal to ax plus bu and y is equal to cx plus du. VL is equal to L di over dt, xi is equal to Vc, I is equal to C dv C over dt, x2 is equal to I, y1 is equal to vc is equal to x1, y2 is equal to ri, which is equal to rv. So equation for the given circuit is x1 is equal to lx2 dot x2 plus cx dot plus x1 over r is equal to u. X2 dot is equal to x1 over L, x1 dot is equal to 1 over C U minus x1 over RC minus x2 over C. So we can write matrix just like A is equal to 2 by 2 matrix minus 1 over RC minus 1 over C, 1 over L and 0. B is equal to 1 over c over 0. C is equal to 1 0 and D is equal to 0. Locally linearize it to define fxu is equal to ax plus bu, where x is a state vector to be predefined and the voltage across C is considered to be only output y of the circuit system, which is measurable. State space model to the transfer function x dot is equal to ax plus bu, y is equal to cx plus du, sxs is equal to axs bu s, xs is equal to cxs plus dus, xs into is minus a is equal to bus, xs is equal to is minus a uh, having a power minus 1 multiply bu and cs, xs is equal to cis minus a having power minus 1 p us plus dus, where ys over us is equal to cis minus a into b plus d is equal to gps. gps is equal to 1 having a row matrix 1 and 0 multiply by s plus 2 by 2 matrix s plus irc ic minus I over l s and 1 multiply by 1 over c over 0 plus 0 gps c 1s minus a into b plus d gps 1 0. After simplification, we got GPS is equal to 1 over S over C plus 1 over CRC plus S over LC square. Now we test the locally linearized system to see if it is stable, controllable and observable. We wrote a code contain the matrix we already wrote here. Let's check the MATLAB code for this project. We linearize the system around a nominal operating point to simplify analysis and control design. This involves approximating our nonlinear system by a linear one near this point. For this, we use MATLAB code to get result by implementing matrix we already formed here. Already we formed here. So we'll clear the previous running code and then we will run this section. We will check stability. Using the place function, we design a state feedback controller that moves the system poles to desired location for optimal performance. We used MATLAB ODE 45 solver to simulate how the system evolves over time from a given initial condition. This helps us to observe the performance of our control strategy. we defined a function which is called system dynamics. Our system function calculates the derivative of state vector incorporating our control law, which is given at the end. You can see. Next, we plot the results. Finally, we plot the output across the capacitor and the control input over time to visually assess system behavior. Through this project, we have successfully modeled and controlled a nonlinear RLC circuit using MATLAB. By linearizing the system and designing a state feedback controller, we have ensured that our circuit meets specific performance criteria. Thank you for watching. If you found this tutorial helpful, please like, subscribe and comment with any questions or topic you would like to see in future videos.